This video is just another opportunity to look at an example of Picard's method. So in this case, we're going to start with the differential equation dy dt equals 3t plus y squared. And we're going to have set the initial conditions so that they are y of 0 equals 1. And that's not the 0, 0 that we've been working with, but let's assume that those are our initial conditions. I'm also going to take the opportunity to show you a slightly different version of Picard's method that you sometimes see if you find yourself watching YouTube videos or looking at a different textbook. You might see this formulaic approach instead. In this version, we have our nth iteration is equal to the integral not from 0 to t, but from t naught to t. I've used the wrong variable there, so let me fix that real quick. Wrong pen. Okay, getting there. That should be a t. Actually, it should be an s, right? And then, so we're going to go from t naught to t. Instead of 0 to t, we go from t naught to t. And what we're integrating is still the function f of s comma y, where y is a function of s. But we're integrating from t naught to t, and then we're adding our y naught value. So let me remind you that this is actually x naught here, and this is y naught. So this would be 1 plus, and then we'll have an integral from t naught to t, and so on. I don't need that there, so I'm going to erase it. But that 1 plus comes from this initial y value. So I have my initial y value, and I have my initial x value, and so I'm going to use those to set up my integral, and I'm going to start with the assumption that y naught, my first solution, or my 0th solution, is my y naught value, right? I've been using 0 because I was assuming that the initial conditions were 0, 0, and if they weren't, that I could shift things around until they were. But this is another approach, and so I'm going to go ahead and stick with that, and that is that this initial value of y becomes the initial guess. It's still a constant, so it's not hard to integrate, or it's not hard to substitute. The integration part, we'll see how difficult that is, but that's my first guess. Y naught equals 1. My 0th guess. My first guess, or my first iteration, is going to be that number. We didn't have that in the previous version. That's one of the differences here. Plus the integral from t naught to t of the function f of t comma y, which is 3t plus y squared dt. However, I need to use a dummy variable because I'm actually integrating on t, so I need to make sure that I don't misrepresent myself or confuse myself. And then the other thing is that y is not just the variable y, but this previous guess, right? So everywhere I see a little y here from my function, I'm going to replace that with the so-called answer or guess from the previous step. So I'm going to take that y out and replace it with, in this case, just 1. Now there's one other thing that I can do here. I'm integrating from t naught to t, but I know what t naught is. I've confused my variables again. This should be t naught. Okay, so since I'm integrating here from t naught to t, I know what t naught is. Remember, we've said all along that t naught is a specific number. We just don't know what it is. Well, this time we do know what it is, right? We're not really speaking in general terms here. This is a general formula for using for Picard's method, but this is a specific differential equation, and this is a specific set of initial conditions. So t naught representing an unknown but constant value. It's not unknown if we have the specific problem. So this time my t naught is 0. So now I can replace this with 0, and I'm going to integrate this. So I'm integrating with respect to t. I don't integrate the 1, and I get 3. Sorry, I'm integrating with respect to s. 3s squared is going to be 3s integrates to 3 times s squared over 2, or 3 halves s squared. I'm going to put this in brackets here. Integrating 1 with respect to s, I get just s. And I'm going to evaluate that between 0 and t. That gives me 1 plus 3/2 t squared plus t. This is my y sub 1. That is a potential solution to this differential equation on these initial conditions. Is it the final solution? Is it the best solution? Hard to say. Why don't we do another couple of iterations and see what we can find out? My second iteration will be 1 plus, right, that's a constant. In this version, I'm adding this integral to whatever my initial y value is. So in this case, it's 1 plus the integral from t naught, which I know to be 0, to t of the function. Now, here's where we have to be careful. This is the function I'm evaluating, a function I'm integrating, right? That's my f of s comma y, or f of t comma y, right? That's the function. So what I need to do is put that function in 3s plus y squared ds. But wherever I see a y, I need to replace that with this, with my previous version. So let me just erase my y squared, and I will replace it with 1 plus 3/2 t squared plus t, and then I have to square that. And that's, of course, I've done it again and forgotten about my dummy variable. Change that to an s, and now I need to integrate this. I think probably the easiest way to do that will be to integrate, let's say, but 3s plus, I'm going to distribute this. I have 1 plus 3/2 s squared plus s all squared. So I have 1 plus, I'm multiplying 1 by all of this, 3/2 s squared plus s, plus, now this times all of this, I get 3/2 s squared plus 9/4 s to the 4th plus 3/2 s cubed, and now s times all of this, s plus 3/2 s cubed plus s squared. That is a disaster, ds. Except that I only have this one constant, but I have multiple s squared terms, so I can add those together. I only have 1/4. I have 2 s cubed terms, so I can add those. There's another squared term. So I can simplify this. Let's do that. I'll just do that on the off screen, and then I'll come back. There you go. That's not really so bad. And it's a polynomial, so it's still going to be straightforward to integrate. My integration will produce 1 plus integral of 1 is s. The integral of 5 is 5s is 5 times s squared over 2, or 5/2 s squared. The integral of 4s squared is 4 times s cubed over 3, or 4/3 s cubed, and so on. I get 3/4 s to the 4th. Let's see, 9/4. So this is going to be to the 5th power, so it's going to be s to the 5th over 5 times 4 is 20. So I get 9/20 s to the 5th. That's a 5. And I'm going to evaluate between 0 and t. I'm actually only evaluating this part because that was the only piece that came from the integration. So I get 1. Now I don't have any repeating powers this time, so it's just a case of substituting my t's in. I have 5/2 t squared plus 4/3 t cubed plus 3/4 s to the 4th plus 9/20 t t to the fourth, and then t to the fifth. This is another potential solution, a closer one than the one I had before, and this one is closer than the one I had up here. Now this time we're not seeing that repeating pattern. I have the 1 plus in both cases, and I do have a t, but I don't have a 3/2 t squared in this one. I have a 5/2 t squared. So I may not be able to do that summation notation trick that I did with the previous example. That's okay. You can't always do that. And if you even if you can, it doesn't always produce something like e to the t or e to the x. It doesn't always produce some nice compact solution or compact representation. So we're just going to stop there on this one. The point of this video was to do another example. I could do another iteration of this. I could do y3, and I'd have 1 plus the integral of all of this, having changed the variable to s. But that's just getting, kind of complicated for the sake of getting complicated. So I'm going to leave that there, and I'm going to say that for our purposes, this is a reasonable approximation of the solution, the particular solution to this differential equation.